thermal one. So now, first of course, you have to know what is thermodynamics. Okay, it is about energy. It is a science of energy. So when we talk about energy, there are various or there are different types of energies. Okay, namely, the most important one here for thermodynamics is first is work done. Okay, the work done. Two is the heat energy. Three is kinetic energy. Four is potential energy, internal energy, okay, and etc. etc. Okay, so these are basically the type of energy we are looking at in thermodynamics. But it should be more than that. But then basically we are looking at this few. Heat, the most important one is between the heat and the work, the kinetic energy, and the potential energy. So thermodynamics is the science of energy. Now, what is energy? I think by now everyone should know what is energy. Energy is the ability to cause changes. Energy is the ability to do work. Okay, energy is the ability to cause changes or the ability to do work. Then, what is thermodynamics? Now, in Greek, okay, thermo means heat, and dynamics, you know, dynamics means the power. So I think this mostly you should have already known these three important points here since you have done thermo 1. Now, then we have the conservation of energy principle, or the principle of conservation of energy. So during an interaction, energy can change from one form to another form, but the total amount of energy must remain constant. Now, this conservation of energy principle is also referred to as thermodynamics first law. Okay, also referred as thermodynamic first law. So in this conservation of energy principle, they say that energy, especially energy, cannot be created. Energy cannot be destroyed. Okay, energy changes from one form to another form. So like for example, changing from heat energy to work done to heat energy, or kinetic energy to work, or potential energy to work, and etc. etc. So that is what it meant by energy changes form. So the total amount of energy remains constant. For example, now when you look at this diagram here, now this is a boulder or a rock, okay, that is on top of this hill here, okay, on the hilltop. So actually at this position here, when the rock is at this position here, when you look at the total energy here, is 10 plus 0. Now this 10 units here is the potential energy. And we know that potential energy is actually based on the height. Based on the height, vertical height, okay, or the vertical position of the object above sea level. So based on this, okay, you might have 10 units of potential energy. But initially, this thing here, this object here, does not move. So it has 0 kinetic energy. So when it starts to fall, okay, when it starts to fall from the hill, okay, what happens is the position of the object from the sea level, the position of the object from the sea level will keep changing until it reaches this position here, or until it touches, or until it goes underwater. So what happens is, okay, since there is a changes in vertical height, there will be a change in potential energy. So let's say, for example, 10 units becomes 7 units because the height or the depth changes. Okay, so there is a decrease in depth or height. Okay, so there is a decrease in potential energy. I repeat once more, potential energy is a function of vertical height. So when there is a change in potential energy, there is a gain in kinetic energy because the object start to move. So let's say we have a gain in kinetic energy of 3 units, whereas the potential energy has undergone a decrease by 3 units. But then when you add up 7 and 3, you still get 10. So as you compare 10 here and 10 here, this is 10 plus 0. This is 7 plus 3. So the total is still 10 and 10. So that is why we say the energy always, the total amount of energy must always remain constant. The total amount of energy must always remain constant. So that is what it meant by the conservation of energy principle. The total energy must always remain constant. Okay, so and also you see here from basically from this diagram, you can also say the gain in kinetic energy, the gain in kinetic energy is actually equals to the amount of energy lost in the form of potential energy. The energy gain in the form of kinetic energy is equals to the amount of energy lost in the form of potential energy. Okay, so based on the conservation of energy principle, so you can say total amount of energy must always remain constant, and also you can say whenever there is a gain of energy in one form, whenever there is a loss, okay, whenever there is a loss or a decrease of energy in one form, there is always equals to the amount of energy gained in another form. Okay, that's conservation of energy principle, or the first law of thermodynamics. So energy cannot be created or destroyed. Everyone should have already known this. Okay, that is also the first law of thermodynamics. Now, the second law of thermodynamics, here we are just briefly going through each of the terms that we are going to use. And I am just revising, okay, with you, okay, on the first few lessons on what you have done in your Thermo 1. So the second law of thermodynamics asserts that energy has quality as second law has quality and as well as quantity. Now thermodynamics thermodynamics first law only looks at quantity. It doesn't look at quality. Okay, it only looks at quantity, thermo 1. But thermo 2 looking at both the quality and the quantity. The quality, such as how to measure the quality of energy, then you have to look into the efficiency of a particular device or component, okay, in order to get to know what is the quality, okay. So and then quantity, of course, the magnitude, okay. Now, second law actually refers to the energy, says that the second law of thermodynamics says that the energy has quality as well as quantity, and the actual process occur in the direction of decreasing quality of energy. Now, what is classical thermodynamics is actually the macroscopic approach to the study of thermodynamics that does not require the knowledge of behavior of individual particles. So you are looking at the energy level of an object as a whole. That means the whole object itself. Okay, what is the amount of energy within the object itself? It does not refers to each individual particles within the system. Okay, within the system. That's classical. Classical refers to the amount of energy or the energy that is as a whole within the system or the object as a whole. That is called macro. And then of course, then you have macro, of course you have micro. Okay, that goes into statistical thermodynamics, which is a microscopic approach based on the average behavior of large group of individual particles. So that is the difference between statistical and statistical, or macroscopic and microscopic. Okay, so this diagram here just to show you that, okay, the concept of energy. Okay, so and you see here, okay, so this is 6 units. The total input to this cyclist here is 6 units of energy. So if let's say it takes 3 units to do work, then there must be 3 units stored inside of the cyclist's body. So when you add up 3 and 3, it must be equals to the total amount of 6 units that has been, okay, transferred to the body of the cyclist. So the total amount of energy, remember, must always be equals to a constant. So 3 plus 3 is also 6, which is equals to this. Okay? And then the second one is just like this cup of coffee here, hot coffee. So that is also to explain or to show you an example of the first law of thermodynamics. So now, as you can see, if this hot coffee here initially is at 70 degrees, and the environment, that means the air that is surrounding this cup of coffee, let's say is initially 25 degrees C. Now, what is going to happen is there would be a heat transfer from the cup of hot coffee to the cool environment. So, of course, there will be energy loss in the form of heat from this cup of hot coffee to the colder environment, that is the air. So the air, the surrounding air, of course, will have a gain in heat energy. And then for the cup of hot coffee, there will be a loss of heat energy. Now, according to first law, okay, remember the total amount of energy lost in one form must be equals to the energy gain in another form. Or you can also say when there is energy loss from one object, if both objects are in close contact, if there is energy loss in one object, that must be always equals to the amount of energy gained by the other object, which both objects are in close contact. Okay? So, one, hot coffee will be subjected to a drop in temperature. The air or the colder environment will be subjected to an increase in temperature. Now, these are some area of thermodynamics, applications of thermodynamics. So we will just look into, okay, each of these, not in detail. I'll just briefly go through. Okay, human body, we are not looking at. In our studies, we will not be looking at human body. So human bodies is also one of the area of thermodynamics application. Now, wind turbines, no, but then wind turbine is also an application of thermodynamics. Aircon, yes, we are looking at air conditioning. We are looking at power plant. We are looking at refrigerators. We are looking at engines, even at jet engines or car engines. Okay, we are looking at engines, power plants, okay, aircon, refrigerators. We are not looking at solar, we are not looking at boat, we are not looking at wind, we are not looking at human bodies. Yeah, but then all these are the applications of area of thermodynamics. Anything any a device or component that involve energy interaction. Energy interaction, that is where you say the application of thermodynamics, where the thermodynamics principles are applied. Now, then the next thing is, of course, you have to know what is system, okay, and its surroundings. What is system, what is surroundings, and what are the boundaries? Now, when you look at this beaker of water here, okay, so if let's say initially, let's say this beaker, okay, has no water in it or no chemicals in it. So this beaker here is empty, and then you have a empty space within it, an empty space within it initially. You don't have liquid in it. So if let's say you pour in some liquid, so the liquid here will take up the space initially which was empty in the beaker. So the liquid has taken up the space. So if let's say we are making a studies on the liquid, okay, if let's say we are making the studies of the liquid that is within, that is inside the space of the beaker. So let's say we are looking at this, we are studying on this. So we will call this, the liquid here, as the system. That's the system. So system is actually defined as the quantity of matters. Matters means things, can be in liquid form, solid form, or gas form. Okay, that is in the space, the empty space, which we choose, okay, or which we select to study. Okay, it's just like, for example, when you're at home or inside your room now, okay, initially is empty. Let's say we want to make a study of the quality of the air that is within the room, within your bedroom. So the air that is in your bedroom will be considered as the system. And the wall of your bedroom, the ceiling or the floor, can be referred as boundary. Okay, they can be referred as boundary. So outside of the boundary, we call surroundings. Okay, why do we need to know what is system, what is a boundary, and what is surroundings? Because we are looking at energy interaction, because thermodynamics is something that deals with energy interaction. When you say energy interaction, that means, okay, we are looking at whether there are any heat energy flowing from outside your room, inside your room, or from your inside of your room to outside of your room. Okay, and then how are we going to identify whether there are heat that is flowing from inside your room, okay, to outside, or from outside the room to inside your room? Okay, how we know, okay, whether there's energy that is flowing across or not? So that is why we have to know which are the boundaries. So anything that crosses the boundary will be recognized. Okay, so that is why we have to know, okay, first we have to identify what is our system, or where is our system, okay, or what is our system. And then we have to know our surroundings, and then we have to know which are the boundaries. So then only, or then we can identify, okay, the energy interaction between the system and the surroundings, which crosses the boundary of the system. Now, system is a quantity of matters or a region in a space which you choose to study. Surrounding is the mass or region outside of the system. Boundary is the real or imaginary surface. If let's say, for example, refers to your room, that means the wall, the ceiling, the floor can be considered as the boundary. Then if let's say doors, do you have doors? Doors, okay, if it is closed, then we can call it as real boundary. If your door is closed, okay, of your bedroom, your door is closed, then that door, okay, can be considered as a real boundary or a real surface. Now, if let's say the door is open, and then you have escaping or going through, okay, the exit, okay, or the bedroom door. Okay, then if let's say the door is open, then it will leave us an imaginary surface there. Okay, we still have to consider that. Okay, but then we call it as an imaginary surface, so that the system, the energy is actually flowing in from inside to outside or outside to inside, crossing the boundary. Okay, so that is for real and imaginary. Now, a boundary of a system can be a fixed boundary or a movable boundary. If let's say, for example, you refer to a piston and cylinder device, we know the piston in the cylinder can move up, can move down. So, but then if let's say, for example, we make a studies on the gases or the air and fuel mixture within the cylinder, that means between the space between the piston and the cylinder head, that particular compartment, that particular section there. Okay, so when the piston slide downwards, okay, it seems like the boundary of the system has increased if the piston slide down. But then if the piston slide up, when you look at the boundary, it looks like it has been contract or it has been compressed. So when you look at these changes here, when the piston move up and down, it actually creating a movable boundary. A movable boundary is actually creating a movable boundary. Okay, system can be considered as a closed or an open system. Okay, I hope you know what it means by closed and what is mean by open. If let's say, for example, your bedroom, for example, refers to a bedroom, and then you are making the studies the quality of air inside your bedroom. If the door is closed, then it's a closed system. If the door is open, then it's an open system. Okay, so from this diagram here, you can see, okay, so the liquid that is in red, okay, and then this tube here is open, so we can call this as an open system. Okay, if let's say you consider the liquid in red here as the system, then the wall of the tube is considered as the boundary, and then when you look at this is an opening. So the when this liquid maybe is heated, it may be able to vaporize, and then particles of this liquid may be able to escape from this, okay, opening here. So we call this thing here such as an open system, and this as a closed system. Hold on. This is a closed system where you can see this part here is closed. Okay, and this we call isolated system. Now, what is the difference between the isolated system, closed system, and open system? Now, when the system is isolated like this, no heat is transferring in or transferring out, crossing the boundary. Okay, no heat is transferring in or transferring out, so it's called isolated. But then when you refer to open and closed, actually energy in the form of heat can go in and can come out. So that is the difference between isolate. But isolated system have to be a closed and isolate. Okay. Now, closed system sometimes is also called a control mesh system. Control mesh system, that means the mass will always remains the same. Okay, no matter whether it is under compression or expansion. Let's say, for example, we refer to a piston and cylinder device where the whole thing is totally closed. Okay, so when even though when it is heated, okay, the air and fuel mixtures within the cylinder is heated or it is cool, when the piston is moving inwards or moving outwards, there will be no escaping of whatever that is trapped within the boundary. That is called a closed system, or is called a control mesh system. That means initially, let's say it's 5 kg. After expansion or after compression, it must still remains as 5 kg. So, okay, and an open system is sometimes called a control volume system. Okay, a control volume system, open system, control volume because of fixed walls, okay, of fixed boundaries because of the boundaries. So the volume is always being controlled. So that is for open system. Open system sometimes is called control volume. Closed system sometimes is called control mass. So when you refer to a closed system, okay, we are not looking at isolated system. We are just looking at closed system. There will be no mass transferring in and no mass transferring out. So the mass must always remain constant. So, but energy, yes, can transfer in and transfer out for a closed system. But if let's say it is isolated, then heat energy cannot flow in and flow out easily. No heat or no heat energy will be able to flow in and flow out if it's isolated system. Close plus isolate. Now it usually encloses a device that involves mass flow. Okay, so an open system, yeah, such as compressor, turbine, nozzle, heat exchanger, and etc. etc. Okay, for open systems. So the open systems, when you look at it, this is a control volume system. This part here are called the imaginary. These are the real boundaries. These are the imaginary boundaries. The real boundaries is something that you can really see. That is the wall of the nozzle, the wall of the thing. And then imaginary is the inlet and the outlet of a nozzle or diffuser or whatsoever device which has an inlet and outlet. Okay, so you refers to control volume. So the mass is, okay, there is a mass flow in and there is a mass flow out. Okay, so and then when you refers to these are called moving boundary. Why we call moving boundary? So when the piston slide inwards, okay, this boundary here seems to be smaller. When the piston slide upwards, the boundary will increase. So it seems like it is moving. But then when you refer to this bottom here, the wall of the pistons, those are called, okay, fixed boundary. These are called fixed boundary. Both mass and energy can cross the boundary of a control volume. This is called control volume. Okay, this is called control mass. Okay, so control surface, the boundaries of a control volume. Control surface is actually refers to the boundary of the, okay, control volume system. A control volume can involve fixed, moving, real, and imaginary boundaries. So you must know what it means by fixed boundary, moving boundary, real boundary, imaginary boundaries. Okay, these are a revision to what you have done in your Thermo 1. Okay.